Good evening, everyone. Yeah, hopefully you can hear me okay because I've moved the microphone position. So if the sound isn't coming through, please do let me know because I also forgot to test it when I got home today. So I really hope it's working. Yes, welcome to Physics with Keith. It's 6 o'clock on a Tuesday. That means it's time for the free online physics tuition session, which is interactive via Discord. And as you can see, the conversation's already started over here on the right-hand side. So if you're tuning on YouTube and you're wondering how you can get involved and participate, then you'll have to click the link, which is in the description below, and join the Discord server. Navigate to the correct channel. This is season 5, episode 3. Navigate to the correct channel, and then you can interact and join in. Of course, you'll need to have your account approved first, and it's always worth trying to do that in advance rather than leaving it to the last minute, because I'm going to be busy during the session and not able to respond to it during the session. Anyway, today we're looking at radioactive penetrating power. And I'm going to start this session by working on some GCSE content. And then in the second half, we're going to take that a step further and look at some A-level content. Now, some of what I'm doing today will involve graph drawing. And if you're a GCSE student and you're thinking, oh, okay, I can switch off halfway through. Well, although the content will be A-level, the skill of being able to draw a graph from the data, that is... Oh, sounds good. Thanks, Dvorak. Yeah, that skill is very much still GCSE, so do stick with it anyway. And so let us get cracking then. I'm just going to switch this over. Here we go. So the first thing I want to show you is a couple of simulations. And the first simulation is one of my favorites. This is one of the virtual physics laboratory simulations. This one came from... this one's been going around for a while now, actually, but it's still there available on the latest version as well. But I think I've still only got version 15 on my computer. Anyway, Virtual Physics Laboratory, the simulations are made by Dr. John Nunn from the National Physical Laboratory, and very kindly gave me permission to use his simulations in my videos as long as I gave him credit, which I have done, and direct people to go and look at the Virtual Physics Laboratory website. You can Google that. It's just Google Virtual Physics Labs, and you'll find the simulations there. Now, what you're looking at here is a vessel, a container, or a simulation of a container, I should say, which contains a ethanol vapor, which is kept at a temperature below the usual temperature where ethanol would quickly condense into droplets of liquid ethanol. So this vapor, you can't see it. It's only when the vapor condenses into little droplets of ethanol that you can see it as little droplets of ethanol. The ethanol is squirted into this vessel just as a liquid, and then it will evaporate because ethanol evaporates at quite a low temperature. But you keep it at an even lower temperature so that it doesn't want to be in that gas state. So it's what we call a supersaturated ethanol vapor. And then what we do is we put a radioactive source in here. Now you can see this here is a simulated Americium source. And that radioactive source just sits there and gives out particles of different sorts of ionizing radiation. And we had a look at some of those last week and the week before. This particular source, Americium, is an alpha source. And there are some keys that some clues that it's an alpha source from what we can see. Absolutely right, Jamie. Alpha, beta, and gamma radiation. So they're the three that we're going to be looking at. But this Americium source is an alpha source. So what I want you to do is to have a look at the trace, that's what we would call it, this path where the radioactive particle has gone, or I should say the particle of ionizing radiation, the alpha particle has gone. Well, how do we know it's an alpha particle? Just by having a look at the trace. So you may know the answer to this, you may not. If you know the answer to this, then in the Discord server, the Discord channel, go ahead and drop a message just to say, well, you can tell it's alpha because, and then just give me the few clues that you've got. If you don't know, then just put a comment saying, no, I don't know. And if I got a lot of people saying they don't know, I'll give you the answer. But it'd be nice if some people can look at this trace and recognize what the telltale signs are that it's alpha. So I'll give you just a moment to type something. And you might not have a clue. It might be that you've never heard of it before. That's part of it, Jammy. That is one of the clues. Although there are particles of radiation that don't go very far and aren't alpha, which you'll learn about in A-level. Yeah, I mean, 5 centimeters is optimistic, Jammy. You're probably more likely in air to get 2 centimeters, perhaps. Yeah, white transit van's not sure. Pranav's not sure. Okay, so there is a few things. The first clue, as Jammy correctly identified, is the short range of a few centimeters, not very far at all. As I say, 2 centimeters is fairly optimistic. 3 centimeters, maybe. 5 centimeters, I think that's maybe a bit much. Although maybe maybe it depends on the energy of the source. Americium, I'm not sure actually, but not very far. A few centimeters. So this is an alpha source with the radiation moving just a few centimeters. That's true, but that's also true for certain other particles. For example, you can get pions that don't go very far, and they're pretty massive as well. So they can pummel along. I mean, not as massive as alpha particles, let's be honest, but they're pretty massive. But you can get other things that are even more massive, like kaons. Which are even more massive and even more exotic, massive particles that don't travel very far but aren't necessarily alpha. So Jammy suggested that it could be stopped by paper, which is true. Alpha particles can be stopped with a thin sheet of paper. But I don't have a thin sheet of paper here. So is there another clue? And the clue, by the way, is this little green symbol down here. I wonder if anyone recognizes this little green symbol at the bottom. Well, I mean, it's a circle with an X through it. So it's similar in the sense that it's a circle, but it's not a voltmeter. It doesn't have a V in it. It's got a sort of an X through it. So Pranav is correct here. If you haven't studied electromagnetism in GCSE yet, and often it's taught towards the end of the course because it's quite a complicated topic. But if you haven't studied electromagnetism yet, then you probably haven't seen this symbol before. But if you have, then you might recognize it. An X indicates that something is traveling into the screen. Whereas if it was a dot in the middle of that circle, it would indicate that something is going out of the screen towards you. So that's an X, so it's into the screen. And what is it that's going into the screen? Well, it's this thing labelled B, which Pranav has said is the field, but that's a bit vague. So what field is it that we label B? And again, this is GCSE level. I like the way you're thinking, Gnome, but we're thinking about fields. And again, this is something that's usually covered at the end of GCSE. So electromagnetic, Jammy, it's part of that. Pranav's correct. It's the last part of that. It's the magnetic field. Now, what you may not yet know, if you haven't yet studied it at GCSE, is that charged particles experience a force in a magnetic field. Not when they're stationary. When the charged particle's not moving, it doesn't feel a force. But when a charged particle is moving through a magnetic field, it experiences a force. And so these particles, we know they must be positively charged because of the direction that the trace is being twisted, if you like, the direction it's being deflected. What direction do you think it's being deflected, just looking at what you can see? Well, we're only looking at the particles that are moving to the right because this container, this housing for the radioactive source, is made out of lead all the way around the outside. So it's only the particles that happen to be moving to the right that we can see. The rest of them just get absorbed straight away by the lead. Yeah, so this to me, Helicopter Boy's right here. To me, it looks like these particles are being deflected upwards. Now, this to me is a problem. And A-level students or students who have studied GCSE and have already done this will understand why that looks like it's a problem to me. What's the problem? Why do I have an issue with this particular simulation? Yeah, it's being deflected upwards, Pranav. If this was an alpha particle, which it's supposed to be, which direction is it supposed to be deflected? It's supposed to be deflected downwards. So I'm afraid, with all respect to Dr. John Nunn, who's created a suite of simulations that are fantastic, but I'm afraid everyone does make mistakes. And on this occasion, I think John Nunn has made a mistake. Because the alpha particle, the alpha particle should be directed... oh no, I'm making a mistake. I'm an imbecile. How dare I assume that John Nunn is wrong? I hope he doesn't sue me for defamation. No, he's absolutely right. I'm being a simple person. Yep, the field is into the page. The alpha particle is traveling to the right. It experiences a force upwards. Now, come on, John. John knows what he's talking about, not me. So what you're doing there is you're using... By the way, the reason why I got it wrong is because I was reflecting in my head to say into the screen like this, so that on the camera it looks like I'm pointing into the screen. In order to do that, I'm pointing towards me, which is out of the screen. So the reason why I got it back to front is because I'm having to put it back to front in my own head to make it work on camera. Anyway, I'm going to sit on my hands so I don't make that mistake again. If you could take out your left hand, if you've not studied electromagnetism at GCSE level yet, you will do. This is new to you. Take out your left hand, which I think, according to the camera, hopefully this looks like my left hand to you. And you get your three fingers and you make them make this sort of shape. This sort of shape here, where you've got your thumb and your index finger perpendicular to each other. You've got your middle finger and your index finger perpendicular to each other. And you've got your, which ones have I missed? Your middle finger and your thumb perpendicular to each other. So all of the fingers are perpendicular to each other, like that. Now this finger, the index finger, this one points in the direction of the magnetic field, which we've decided is into the screen, And this is where the fact that the camera is reflected might mean this doesn't work. So you will have to play along at home for this to work. So the index finger, you need to point into the screen. The next finger is the middle finger. The middle finger points in the direction that the alpha particles are moving, because they're moving to the right, and the thumb will point in the direction that the force is on the alpha particles, and you'll see that the thumb is pointing up. That little rule, which you'll learn about a bit later on, Fleming's left-hand rule, you can use to determine the charge of these particles. If they feel a force up, and in this case they do, then they must be positively charged. At A level, you take it a step further, and you measure the radius of curvature of that path and use that to determine the specific charge of the particle. But that's not GCSE level. That's just a little bit for A-level students. But for GCSE students, you do have to know. It is very, very hard. Dvorak, it's part of the reason. But another part is because the specific charge of the alpha particle is so low. So because the specific charge is so low, because alpha particles have got so much mass, the deflection is very, very slight. Yeah, so Jamie, radioactivity is a general term we use to describe the instability of nuclei. If we have an atom with a nucleus that is unstable, the nucleus can decay to become more stable. In doing so, it releases a part of itself. It releases something from itself. Now, in the case of Americium, it releases 2 neutrons and 2 protons. That's an alpha particle. And that makes the Americium, the daughter of Americium, whatever that is, I'd have to grab a periodic table to look it up, but that makes the daughter of Americium more stable than Americium itself. So it emits an alpha particle. anything that emits an alpha particle is an alpha source. Radioactivity is the general name for this phenomenon where nuclei decay by emitting other particles. So Dvorak, if you're an A-level student, I'm not sure if you are, I don't think you are, but A-level students will learn about specific charge. GCSE students, don't worry about it, just it's because the mass of the alpha particle is so big. And one way to think about it is if I had let's say, a bucket with very little water in it, and I swung it around with a rope, I wouldn't need to pull that hard on the rope to get that bucket to swing around in a circle. But if I filled that bucket with something really heavy like lead, I'm going to have to pull. I thought so, Dvorak, yeah. I'm going to have to pull much harder on that rope. So it needs a bigger force to go in the same circle because it doesn't want to go in a circle. It wants to go straight. And that's what's happening with these alpha particles. They've got so much mass they want to go straight. But I can load this up with a different source. Let's load it up with, strontium. So strontium is not an alpha emitter. Strontium is a beta emitter. The penetrating power of beta radiation is far greater. They've got less mass. They don't interact as strongly with matter, so they can penetrate through matter far more. Alpha particles interact very strongly with matter because of how much charge they've got, the charge of 2 protons, whereas beta particles only have the charge of 1 electron, so it's a bit less charge. They also have far less mass, so they can go straight through matter, hitting less on their way. It's a nice way of thinking about it. Now, it might be difficult to see, especially if you don't have your brightness of your screen up high, but can you see there's a wispy little spiral path appearing from this strontium source? Hopefully you can see that. If you placed a real source, not a simulated source, you wouldn't see one particle at a time. What you would see is, depending on how active the source was, how old the source was, you would see lots and lots and lots of particles. Yeah, no, this is beta minus emission. Absolutely correct. And the reason why this is beta minus emission is because it's got a much higher penetrating power. It travels through the air further, but also it's deflected downwards. And in electromagnetism, you'll learn that that means that the beta particle must have negative charge in order to cause it to be deflected downwards. So basically, if we are very close to a beta particle, we are kind of in trouble. Yeah, not the particle itself, Jammy. A single beta particle isn't going to do a tremendous amount of damage, or the likelihood of it doing damage is low. Our body is very, very good at dealing with mutations on the small scale. It is, sometimes mutations do get out of control, and that's how cancer happens. But very often, we'll have a cell which mutates during cell division. The mutation that it has is not a good one. It causes the cell to die or behave wrongly, and the body will then metabolize that cell. And our body's quite good at doing that. So a single beta particle, worst case scenario, it mutates the nucleus of an atom, causing it to mutates the nucleus of a cell, causing it to reproduce uncontrollably. Usually our body picks that up and deals with it quite quickly. If, however, we were exposed to a beta source, so something that's like strontium, which is constantly emitting beta particles, then our body can't deal with it quickly enough. And then when there's enough cells that are mutated, well, all of a sudden we've got a problem. And as you say, Jamie, then we're in trouble. So it's not so much the radiation, it's the radioactive source. You'll see, for example, people wearing very careful protective clothing. I recently was watching a film called The China Syndrome. It's a great film. You should watch it. But they were with a Geiger counter in the nuclear reactor core, in the building, anyway, the containment structure, not the core, in the containment structure with a Geiger counter measuring the activity of some sludge they found on the floor. Yeah, the biohazard suit. The biohazard suit doesn't block the radiation, but what it does do is prevent you from accidentally inhaling any of the radioactive source. So you're being exposed to beta radiation the whole time you're stood there with the suit on. But when you get out of there, take the suit off, have a decontamination shower. Yeah, it prevents contamination, helicopter boy. That's perfectly worded. It doesn't prevent irradiation. So you've still got to watch out for your dose. So that's a higher penetrating power. You can see they hose you down. Yeah, they do. Exactly, Jammy. So you can see that this particle's traveling a far greater distance through the air. Okay, it's spiraled up, but that's because of the magnetic field. Gamma radiation is very, very difficult to observe in a cloud chamber. I mean, you might see every now and then with this 𝗭𝘪𝗯𝘬𝐶𝐿 source, that was a beta particle that came out of that 𝗭𝘪𝗯𝐶𝐿. But if you watch it, do you see that wispy little strip there? That's supposed to be representing gamma, but I'm not convinced it's very accurate as a gamma emitter. You know, you wouldn't really see a line of those. You'd just see one little droplet appear, and you wouldn't notice it. So you can't see gamma radiation in a cloud chamber. You just can't. No. So the thing about gamma radiation, Dvorak, is it's not charged. So it doesn't matter what the magnetic field strength was, the gamma radiation wouldn't be deflected by it. It would just travel straight through. My issue is that gamma radiation works differently to alpha and beta. So with alpha, the particle's going to pummel its way through the air, and every time it smacks into an atom or a molecule of air, it ionizes it, slowing down the alpha particle a little bit in the process. And so it goes bang, 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 bang through the air, slowing down until it's too slow to actually cause any ionization anymore. Then it's just a helium nucleus, and it leaves a wake of charged particles, ions, in its path. That's why it's called ionizing radiation. And the same is true for beta, although it interacts less with matter. With gamma radiation, a gamma photon, if you like, a particle of gamma radiation, is absorbed. And it's either absorbed or it's not absorbed. It can't just go bang, 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 bang through matter. It's just absorbed. What you can get after that absorption is the emission of things like X-rays or other sorts of electromagnetic radiation, which are high energy. But you wouldn't see, like you see in this simulation, sort of a very thin wispy cloud of lines. You wouldn't see that. So I'll just read some of these messages that I've missed. Gamma radiation, just a photon. Yeah, exactly. They don't have charge. And there's a gamma particle. Lots of energy. Yeah. What differentiates a gamma photon from an X-ray photon? Remember, a photon is just a particle of light. It's another way of thinking about light. What differentiates an X-ray photon from a gamma photon isn't the energy, it's where it comes from. A gamma photon comes from the nucleus. Is that why when you have X-rays, everyone runs away? Yeah, exactly. Because X-rays are ionizing radiation. They're very, very high energy. And some helicopter boy, that's true. In terms of more energy, no, more energy equals lower wavelength, which Pranav's picked you up on. But it's true that usually we teach visible light, ultraviolet, X-rays, gamma rays. And it's true that the most energetic gamma rays have more energy than the most energetic X-rays. That's true. But what really separates them is where they're from. Because it is possible to get X-rays with higher energy than electromagnetic radiation emitted from the nucleus. There is an overlap. He meant higher frequency. Yes, he did. Yeah, he did. Okay, so that's the first simulation, and we've had a little look at... Thank you for that, Pranav. It will hopefully come through. Yeah, it is. That came through nicely. So we've had a little bit of a look at penetrating power of alpha and beta and gamma. Gamma, very, very penetrating, infinite range, using this simulation. We're now going to switch across and look at a different simulation, which will allow us to extract some numbers. We're going to do an experiment together. So I hope that you've got something to write some numbers on, maybe some graph paper. If you don't, then you might have something like Microsoft Excel. Other spreadsheet packages are available that you can use. But we're going to do an experiment together. And this is still GCSE level at the moment. It gets to A level when we analyse the results. Now, In this simulation, I believe the Geiger counter here, through the power of magic, does not include background radiation. I could be wrong. If I'm wrong, well, we'll soon find out because there'll be a systematic error on our final results, but that's an A-level thing. But I think by the power of magic, background radiation has been removed from this. I see a few people are typing messages there. What I can do... Yeah. It's a lovely, lovely piece of equipment. And if you've got radioactive sources in your school, by law, you have to have one that works. And it's a jolly good idea to have a backup, because as soon as it stops working, you're breaking the law. Anyway, Pranav, I can't do that because I can't remove the source. The simulation doesn't allow me to. Dvorak, even in that situation, there would, even with thick lead, there would possibly still be background radiation. Believe it or not. Yeah, Jamie, there are lots and lots of rules. I believe it's L93, CLIAP's guide L93, but I can't remember. But there's loads of rules. It's a 100-page document all about how to handle radioactive sources in schools, and there's good reason for it. I'm going to take a small sidestep here because this is a good story. I'm going to tell you two stories. The first story is about something that happened in Brazil in the 1980s. Can't remember exactly when. I think it was 1987 or something like that. So what happened was a hospital was moving site. A private hospital was moving from one building to another. And partway, this is a true story, and partway through the move, there was some legal dispute about ownership of the building, the old building. And while that legal dispute was going on, the hospital couldn't move any more equipment. So they were set up in this new hospital, and some equipment was still left in the old building, which was being kept under guard by the person who owned the old building. Now, unfortunately, the guards weren't always there. So knowing that the guards weren't there, a couple of bandits, burglars, broke into the old hospital to see what they could salvage and sell. And when they broke into the hospital, I'll put no full face for this. When they broke into the hospital, L93, there we are. Thanks, Pranav. What did I say, L93? I hope I said L93. Anyway, when they broke into the hospital, they stole a few things. One of the things they stole was a canister about this size, a big canister, which was very heavy. I mean, it had lead in it. It was all encased in lead. So they thought they could scrap metal and sell it. I said L92. I was so close. Thanks, Pranav. They thought they could take it apart and sell the scrap metal. That's what these bandits thought. So on a wheelbarrow, they took the radioactive source that's used for radiotherapy and carried this radioactive source off home, being horribly irradiated all the time. They seemed to be unaware of what was going on because they got very ill and were vomiting and had sores on their skin and all this sort of thing, whilst they were taking a hammer and chisel to this thing and shoving screwdrivers in it to try to separate out the scrap metal. At one point, they broke into it and could see a blue light coming from inside. That's the air ionizing because of the high energy ionizing radiation inside this thing, the blue light. They thought it was something supernatural or spiritual, some bizarre box that contained some ethereal magic. So they shoved screwdrivers in it, scooping it out. They tried to burn it to see if it was a new experimental kind of gunpowder. That's the benefit of hindsight, Jammy. Now, unfortunately, they both died. Also, most of their families and friends died because they invited them around to have a look at Ghost Energies. They invited them around to have a look at this thing. Not only that, the cleanup operation had to excavate a tremendous amount of top layer of soil from all around where they lived. The whole place had to be basically closed down during this process, because what they were hacking away at inside this lead box was a cesium-137 source. A very, very nasty source indeed. And as I say, they all died. They didn't know that's what it was, Dvorak. They didn't know. That's why you should do your GCSEs. Right, the second story I'm going to tell you happened in, I believe it was still Soviet at the time, but it's now modern-day Ukraine. But at the time, it was part of the Soviet Republic of whatever it's called, the USSR. And this was not anyone's fault as such, although I would argue that perhaps it was. You may have heard about depth measuring apparatus. Yeah, half-life about 30 years. That's right, Gnome, yeah. So, depth measuring apparatus, I'll draw a quick sketch of how it works. It's related to penetrating power. Essentially, if I've got a machine and I want to know how deep something is, one way of doing it is to have a radioactive source at the top. Let's do this. A detector at the bottom, like this. This is my radioactive source. I'm going to do my best at drawing a radioactivity symbol now. I've changed the screen resolution of my little screen, so I can't really see it very well. There we are. That looks good. This is my detector. And you have something in between that you want to measure the depth of. The classic example at GCSE level is aluminium foil on a conveyor belt running through with perhaps 2 rollers that can squeeze it down to make it thinner. And what happens is if the amount of radiation detected at the detector goes down, it means that the aluminium foil is too thick to squeeze the rollers closer together. But if the detected radiation goes up, it means the foil is too thin, so relax the rollers, separating them out a bit. So this is a standard sort of, the radiation goes through like this. This is a standard sort of thickness measuring thing. And you find these all over the place. And this particular one was in a quarry, where presumably they were using it in silos to tell how much whatever the quarry was using, whatever the rocks that they were getting, how deep that was in these silos. Unfortunately, the radioactive source somehow got damaged. And it fell into the rocks below. And got ground up. Of course, the source container was all still there, but the source was all exposed. That then went on to become concrete. That concrete then ended up in an apartment building. This is all true. You can look this up. It was again cesium-137, and it ended up in an apartment building in the USSR, in modern-day Ukraine, and sat there in the walls. It wasn't just dust, it was quite a lot of radioactive source, enough that people were reporting increased cases of leukemia, getting very, very ill, especially in the apartments either side of this wall. Several people died before they discovered that there was actually a capsule containing cesium-137 in the wall. Yeah. It's really sad that things like this happen. It really is awful. There are people who oppose the use of radioactive sources for things like sterilizing medical equipment or sterilizing food so it lasts longer on the shelf. There are people that oppose that. And the wrong reason to oppose it is, I'm scared of radiation because you might contaminate the food. Well, radiation doesn't contaminate, radioactive sources do. So the wrong reason is the same reason why certain people of a certain generation are scared of microwaving food in case the microwaves get stuck inside the food. It's just nonsense. The microwaves do not get stuck inside the food. I don't want to eat that. It's radioactive. It's been in a microwave. It's a jack of potato. It'll be fine. That's the wrong reason to try to avoid irradiation and sterilization technologies. The right reason is that, unfortunately, radioactive sources do escape. They do end up where they shouldn't be. And the consequences are lethal, which is why, circling back to, I think it was what Jammy said, radioactive sources in school are kept under very, very tight. The purpose of microwaves is to microwave food, though. That is true. It's something that could have been avoided, Jammy, absolutely. But it's the reason why schools have tight controls, right? L93, that document, has to be followed. Why there's a document that has to record when sources are used. Every year they have to be inspected. and check the containers and everything for risk of contamination, make sure they're not damaged and leaking. There are some very strict rules in place for the use of radioactive sources. If you use a radioactive source in the lab under direction of your teacher, it's as safe as anything is. It really is. Teachers use them all the time, and the rate of teacher death from cancer is not significantly higher than the rest of the population. So it shouldn't be an increased risk. The risk is if a source goes missing. And that's why there's such tight controls, to make sure the sources are all accounted for, and to make sure that accidents like what happened in USSR, like what happened to Brazil, and there's been other occasions, accidents don't happen. Of course they do. And that's why some people think that radioactive sources should be banned. Chernobyl is a special case, and I could spend a whole session talking about Chernobyl. Nuclear disasters is one of my favorite topics to talk about. But I'm going to get on with this experiment because we've only got 24 minutes left. So let's do this. What I'm going to do, I'm going to time for... I'll see how long. I might just do it for 10 seconds or something. I don't suppose it really matters at first. More than that helicopter boy. It was awful. Anyway, let's start with nothing blocking the radioactive source. Let's start with that. So I'm going to press go. And you can see the counter is measuring that there are particles of beta radiation getting from the source into the counter. How long should I do this for? What do you reckon? I mean, really, we should do it for 2 minutes, but I don't just want to sit here staring at this for 2 minutes. So should we just do it for 30 seconds? Who needs proper safety checks? Not the Russians. Yeah, okay. I'm not going to go there. Okay, so 30... Oh, how's that? Stopped it dead on 30 seconds. So, if someone could please calculate for me what the activity is of the source with nothing blocking it. The activity of the source. Anyone happen to know what the activity of the source is? Oopsie. So the way you'd calculate the activity, and this is something you need to know for GCSE level, is the number of counts, in this case it's 151, divided by the amount of time, in this case 30 seconds. So 151 divided by 30, which, as Pranav and James and Gnome and Dvorak correctly said, is 5.03, and they've got the unit, although Gnome's unit is incorrect, but Dvorak, James, and Pranav have got the correct unit, becquerels, counts per second. Gnome, can you see why your unit is incorrect? There we go. Yep, capital B. So that's the first one. So please make sure you write that down. Let's move on to 1 millimeter thickness of lead. Is it lead? Aluminium. 1 millimeter thickness of aluminium. AKA becquerels. Okay. Okay, so let's reset this. And I'll start it. Off we go. And you can see, you can probably get a feel for this. The number of counts is not going up as quickly as it was before. So in 30 seconds, we'll see how many counts there are. And we can convert that into an activity. Do you reckon I'm going to be able to freeze it dead on 30 seconds again? I don't think I'm going to. It's very exciting. 29. The greatest man alive. Look at that. There we go. So 1 millimeter thickness, and we've got 109 counts in 30 seconds. And it looks like 𝘭𝘪𝘯𝘬𝘴 wanted to get in there first. That was some quick reactions. Well done, Gnome, as well. So 109 divided by 30 is indeed 3.63 becquerels. Well done. Let's increase the thickness to 2 millimeters. And reset and start. Now what we're going to do is we are going to see what the relationship is between the count rate that is measured and the thickness of the aluminium. And you might already have some idea of what that relationship should be. You might already have some sort of idea. If you are an A-level student, I'd expect you to have some sort of idea as well. 1 second. Oh, what is happening? It must be automatic, so it rounds to near a second. 62 divided by 30. Look at that. Okay, so it looks like 𝗭𝘪𝗯𝘀 is incorrectly rounded. Everyone else, I think your answers are fine. 𝗭𝘪𝗯𝘀𝘀 has changed it. Okay, so if you're an A-level student, so we're going to sort of start mentioning some A-level stuff now. If you're an A-level student, then it's quite likely that you have done, or that you've got on the horizon something to do, the inverse square law for gamma radiation practical. It's a great practical to do. Do you think that the relationship here will be an inverse square relationship? So if you're an A-level student, you know what I mean by inverse square. You've got an idea for what's going on, so you might be able to answer. If you're a GCSE student, you're probably thinking, what? Inverse square just means that if I double the distance between the source and the detector... 1 second. Look at that. That is some... It must be... Because no way I've got it right 4 times in a row. Yeah. So inverse square means that if I double the distance between the detector and the source... yes, I got 0.8 becquerels as well. Although, yeah, no, I'll go with that. 0.8 becquerels. If I double the distance between the source and the detector, then the activity that is detected falls by 1/4. If I increase the distance by 10 times, then I get 1% of the activity detected. That's what we mean by inverse square. Jamie says, I challenge you to do it on a proper stopwatch. Yeah, I'm not going to be able to do it. No chance. 27, 28, 29. Oh! So close. Oh, I'm disappointed with myself. I'll have to remember that that one there is not 28 divided by 30, which would give me 9.333 blah, blah, blah. It's 28 divided by 29.8, which gives me, to 2 significant figures, it is a different number. Oh, I'm so upset with myself. So upset. Okay, ready for the last one? Oh, I didn't change the thickness either. Oh no, I didn't change the thickness. What am I doing? I did 3 millimeters twice. All right, well, let's just do 4 millimeters then. Oh, what am I doing? Nearly got all the data anyway. And you're writing them down, so I might have to ask you. How many becquerels for the first 3 millimeters? Well, do 24 divided by 30. Or you can do 28 divided by 30. I mean, this thing about radiation is there's a randomness to it. 12. I got it that time. Yeah, the thing about radiation is there's a randomness to it. Yeah. Good stuff. And then, I'll tell you what we can do. Should we do 5 and 6 just for completeness? There's no more room on this table, so I don't know what will happen if I click store. But just for completeness, let's do 5 and 6. Hopefully you're writing all these down. And then, because I'm not writing them down, and then we'll see about getting a graph drawn and we'll see about making sense of it. And at that point, GCSE students, as long as your graph is okay, will, good stuff. If you are a regular participant, you are able to share the picture of your graph via Discord. Okay, if you are not a regular participant yet, you won't be able to share the picture, but you can hopefully become a regular participant. Pranav says, is it an exponential relate? What? I wasn't paying attention. Reset. Let's try it again. Pranav says, is it an exponential relationship? Well, you tell me. You tell me. Sly reckons it might be an inverse proportion, so you disagree with each other there. It's fascinating. And do you know how much physics work is spent just watching numbers? It's what we enjoy doing. Far too much time watching Sesame Street as children. 4 divided by 30. That is a low count rate of 0.133. And 6 millimeters. 6 millimeters. Start. Good. So, yeah, as I say, if you want to start making the graph as a GCSE student, then you can share it on Discord. I can see it. I can critique it. I can say what's right about it. I can say what's wrong about it. If you're an A-level student, you're going to have to think carefully about how you're going to adjust your data to get a straight line. That's what we care about. You might even want to think about 1 divided by 30. You might even want to think about what you would do. What you would do to check if it's an inverse square or an inverse relationship or an exponential decay, which is what Pranav thinks it might be. Where can you find graph on Excel? I'll show you, Jamie. Don't worry, I'll show you. So you've all got your data. You're all chugging away now, hopefully. 1 divided by 30. Did we do that one? 0.0333. So let's load up Excel. And hopefully my computer's GPU isn't going to start smoking if I've got too many things running at the same time. No, I closed it. I don't need it anymore. I don't keep things open I don't need. That's a recipe for disaster. Okay, so this is Microsoft Excel. One of my favorite programs. I do love Microsoft Excel. Where'd it go? Let's close that down for a second. No, that'll do. And let's have the formula bar so we can all see it. Hopefully not. Right, okay, so data. We've got thickness in millimeters. What would you have? 1, 2, 3, 4, 5, and 6, I think it was. And then we've got counts here. And I didn't write any of them down. So, well, let's put count rates. Let's put count rates in becquerels. So hopefully I'll be able to scroll up the chat now and see what they were. 5.03. And then it was 3.63. And then it was 2.07. And then it was 0.8. And then it was... it's still 0.8 because that was I did the one twice because I'm a moron. Then 0.4 for 4 millimeters. Hang on. .0333 was one of them. That one was 0.13. I'm missing one. What was 4 millimeters? 0.4. Thought it was 3 millimeters. Oh, I know what I've done wrong. You see? Did I say I was a moron? I did. There we go. Absolute plonker. 0.8. There we go. So, I can see Dvorak's graph. Yeah, it looks okay. Can you tell from that whether it's an inverse square, or an exponential decay? Now, to draw the graph, this is what you do. You select your data, you click on Insert, and then you have to be careful with this. You don't want to do a line. Absolutely crucial you don't do a line. If you do a line, then and even if you set what the x-axis should be in values, it will assume the x-axis is a categoric variable. Now, in this case, it wouldn't really matter because your x-axis would be all evenly spaced. But if your x-axis values aren't evenly spaced, it produces a nonsense graph. So as physicists, the graph that we want most often is going to be the old scatter. There it is. Can you see it okay there? Hopefully you can see that okay. I'm not going to bother labeling the axes because I'm a lazy scumbag. Yeah. So if I add trend line now, what we can do, if we're just not sure, is I could do that and say, this is what an exponential relationship should look like. Is it linear? No. Logarithmic? Can't do that. That doesn't fit. No way we can get that to work. A power law of some sort. That would be like your inverse power. Where's it gone? Add trend line. No, doesn't want that either. So it's happy with exponential decay. It really isn't happy with anything else. Which is kind of a clue here, isn't it? It's kind of a clue that it's probably going to be some sort of exponential decay. So that's about as far as it would get at GCSE level. Now at A level, we would have to confirm this is the case. So A level students, what would I do to this data to turn that into a straight line? That's it. Oh, Pranav, you hero. So you may not be able to see it very well because it's just got lofted to the side of the screen. But what Pranav's done here is he said A is proportional to e to the power of kd. He's then put a constant of proportionality and he's logged everything, saying that the log of a constant is still a constant. So yeah, he's just added there. C is just a constant. Yep, so Jamie, that is now. This is now A level. What you can see Pranav has put here is A level. This graph showing how the activity falls as the thickness of the aluminium increases, that's GCSE level, and appreciation for the fact that it's not a case that after a certain thickness the source switches off and at a lower thickness you get detection. The idea that it falls away exponentially, that's GCSE. Everything else now is A level. Super. Thanks, Jamie. It's good to see you. Good. I'm glad you could make it. Yeah, Pranav's right, though. He's not fussed about the constant. So should we do it? Should we see what happens? Let's move this thing out of the way. So equals log. Do you reckon that's a natural log? Log? I think it should be. Equals log of that. Oh, no. Why is that not working, he says. Hor, 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 hor. Actually, that's a good question for A-level students. Oh, is this GCSE students tuning out? Okay. By GCSE student, you can stick with it, but okay. Equals log. I'm going to look back at the at what's going on later and wonder why everyone's left. So you say log everything. I've logged everything. First of all, why is this giving me an error? Yeah, of course you can't. Why can't you? What does it mean to do a log of something? And this is log to the base e. What does it mean to do a log of a number to the base e? So this is log to the base e of d, the thickness d, and this is log to the base e of the activity that's detected, or the count rate, should I say. So what does it mean to do the log of something? Because if you understand what that means, you'll understand why you can't do log of 0. Right, okay, Gnome. So what's x? Pranav, yeah, I think what you said makes sense. I think so. So Gnome, what did x equal? Yeah, log to the base x. So it's log to the base e. So what do you raise e to the power of to get 0? There isn't a solution. There is nothing you can do. But as I think it was Pranav, can't remember who said it. Yeah, just the dependent variable. Yeah, Gnome is right. We're not going to log this one. We don't need to log this one. If we now plot, if we go into select data, and instead of the y values being those, you make the y values those, we get what looks like a perfectly straight line, he says, slightly tongue-in-cheek. Look at that, what a perfectly straight line. I don't know what to make of that. It's, yeah. It's Dvorak, I would agree with you, except this is definitely a curve. Right, no, but that would be a random error. And so you'd expect to see points randomly scattered about the line. But that's not what we've got here. What we have got is a curve. What does that indicate to us if it is a curve? It goes back to something I said right before we did the experiment. Systematic error, absolutely. This is not a random error. This is a systematic error. And what do you think the source of this systematic error? Dvorak's got it. I said it's a detector, but due to the power of magic, it removed background radiation. This suggests I was wrong. So what I might be tempted to do now, and I don't know if it's going to work, but what I might be tempted to do is to remove background radiation myself by doing this equals that, subtract that. Well, I mean, at that thickness, we've got nothing intelligible. And now everything's gone wrong. Super. So let's reduce the range of the results. Select data. What's that say? 58? Let's change that to 7. 7. Yeah, it didn't work as I wanted it to. Problem solved? There's still a curve. Yeah, absolutely. There is still a curve. So that wasn't the source of the systematic error. So now we have to think carefully, well, what is the source of the systematic error? And I don't know the answer to that. It could be issues with the detector itself, although the distance didn't change, so that shouldn't matter. I'll close the simulation now. It could be that the source was not only emitting beta radiation, and so there's more radiation getting through, although we did subtract the maximum thickness of the aluminium, so I'd have thought that would have taken that into account. So the short answer is, I don't know. I'd expect it to be an exponential decay, but it's not. So you've got the data, play with it, see if you can make sense of it. I'm very keen to know what you come up with. I'll have a think about it as well over the next week. Drop a message on Discord if you figure it out. I do love a challenge. Don't just walk away and say, oh, well, I didn't get it. If you're an A-level student, really try and make sense of what's going on here. You've seen the simulation, you've got your data. Can we understand why we're getting a curve when we expect to get a straight? And that's all I've got time for. So thank you very much for tuning in. I do hope it's been useful, even though the experiment yielded some odd results. I think it was still better to get that than to not. At least we've got something to think about. If you are just just sort of tuning in for the first time and thinking, I look like a lot of fun interacting, I want to interact with that, then you can go ahead. You can subscribe to my YouTube channel. Just make sure that's right. Yep, you can subscribe to my YouTube channel, get onto Discord and get yourself turned into a participant. Especially if you think you might know why this strange effect was happening, then you can get onto Discord and let us know what you think. And I will see you next week. Have a good week. Stay safe.